Hey everybody, this is Mr. Piercy, and in this video what we're going to be taking a look at are how we actually use some of the properties of uh, kites and trapezoids, and particularly what we're going to be looking at will be isosceles trapezoids. Well, a trapezoid is a quadrilateral that only has one set of parallel sides, which is, we're branching away from the parallelograms that we've been talking about. Then we have the bases of the trapezoid. Well, the bases, those are the sides that are actually make up the parallel sides of the trapezoid. The base angles are going to be angles that are formed using those two parallel sides. And the legs of a trapezoid are the ones that are not parallel. Here, let me go ahead and blow up this picture. It still may be a little bit blurry, but we have the two bases. We have, let me pick a color we can see here. So we have these here, those are parallel to each other, and the base angles here and here, here and here, and I know they're not the same, but I'm just trying to show you where they are. And then we have a mid segment, also be parallel, but I just wanted to blow that up, make it a little bit easier to see here. Now, as for an isosceles trapezoid is going to have legs to be congruent to each other. We have the mid-segment. Now, we've seen the term mid, we're studying triangles. And a mid-segment at that point was defined as a segment that connects two midpoints together. And that's exactly what we're seeing here. Now, technically, we have more than one mid-segment. I could, let me add this here. I could say that here is a midpoint and here is a midpoint, so this would be a mid-segment also. However, we will never talk about the mid-segment between the bases of a trapezoid. It will always, anytime we're looking about the mid-segment of a trapezoid, it'll always be the mid-segment of the legs. And that's because the mid-segment that goes to the legs will be parallel to the bases, and it has some unique characteristics about it. Now, as far as a kite is concerned, there's some extra information I'd like to add to here. So essentially, a kite is two isosceles triangles that share a base. So we have angle A will be congruent to angle C in this case, because ultimately this part here, angle BAC, and this part here, those would be the base angles of triangle ABC. Same thing with angle DAC and CDA, I'm sorry, DAC and DCA, those would be base angles of an isosceles triangle. So together they're going to be congruent to each other. AC, I would call that the non-vertex diagonal. I can't spell right now. Non-vertex diagonal. So if we added in this segment here, BD, BD is the vertex diagonal. And we would call that the vertex diagonal because, again, if we look at it as an isosceles triangle, triangle ABC, well, point B would be the vertex of the triangle because that's where the two legs come together the two congruent sides come together to form that angle. That's what the vertex angle is. So AC be considered the base of the isosceles triangle. Well, same thing with point D. It would be considered the vertex of its isosceles triangle. And since BD is the diagonal that connects them, that's called the vertex diagonal. The vertex diagonal is also the diagonal, or it's also the altitude of the isosceles triangle. So it will bisect the vertex angles just like it does in an isosceles triangle. And it will make it will be a perpendicular bisector to the non-vertex diagonal. So make sure you include some of that information into your notes. So that way, when because you're not going to see everything in these set of notes, but those are properties that you should be aware of. And a lot of it has to do with the fact that a kite is essentially just two isosceles triangles that share a base. Now here we're going to be looking at a figure where I'm asking you to justify what type of figure it is. Is this a trapezoid? Now, a characteristic of a trapezoid is that it has only one set of parallel sides. So if I'm giving you something like this on a graph, or I'm just giving you coordinates of a figure that could be a trapezoid, what you need to be able to do is justify it is or it is not by using the slope. It is unacceptable for you to say, yes, this is a trapezoid because it looks that way. So what we're going to look at is we're going to look at the slopes of the opposite sides and see what we wind up getting. Well, hopefully you remember your slope formula, y2 minus y1 over x2 minus x1. And when we plug in the numbers for the slopes of DE and CF, we do see that they both have a slope of 1/3. And since the slopes are the same, that means those two segments will be parallel to each other. So we at least have one set of parallel sides. So moving on to the second set of segments, EF gives us a slope of a -1, while CD gives us a slope of a +3. So they are not parallel to each other because their slopes are different. So because I have one set of parallel sides in this particular quadrilateral, then I wouldn't be able to justify saying that it is a trapezoid. Now here are some properties specific to isosceles trapezoids. Because trapezoids in general, there's really not that much unique about them other than maybe the mid-segment formula and the fact that the same side angles have to be supplementary. And we haven't gotten to the mid-segment formula. We'll get to that here in a second. Now, isosceles trapezoids do have some more unique things about them, which means that they get used more in problems that you'll see on your assignments and quizzes and tests and so forth. Well, because the legs are congruent to each other, the base angles will be congruent to each other, just like they are in an isosceles triangle. So angle B and C are the same because they're base angles from the same side at the same base. And same thing with A and D, they would be congruent to each other. So in the next one, the one in the middle, what that's telling you is that uh, if I happen to have a trapezoid where I have a pair of base angles that are congruent to each other, in this case meaning A and D. If I tried to say A and B were congruent to each other, well, those wouldn't necessarily be base angles in this diagram, so we wouldn't want to go that route. But if I gave you angle A and angle D congruent to each other, or I gave you angle B and angle C congruent to each other, then you could say, oh, I have an isosceles trapezoid. And the last one is unique, again, because this is only the second quadrilateral that you're going to see, where it has diagonals that are congruent to each other. The only other quadrilateral that we've seen so far that has that characteristic is a rectangle. And that is a very important piece. It's something that is, I don't know, I kind of like asking questions about it, and it's something that a lot of students don't really pay a whole lot of attention to. So I'm hoping that by mentioning that to you, you'll pay a little bit closer attention to it. So isosceles trapezoids have diagonals that are congruent to each other. All right. So let's see. What I want to look at here in this particular problem, again, try not to pay too much attention to the solution material as we go through it. Just pay attention to the information that's given to you in the diagram itself. See if we can think our way through the problem. So we have this shape for a kitchen shelf, and we want to know what are the measurements of the angles that are missing. Well, because it's isosceles, and I know it's isosceles because they give me these hashtag or not hashtags, but those little hash lines that are indicating that it's isosceles. Well, that means angle K and angle N have to be the same. Well, that means this one has to be 50. Well, so we got two of those angles. Now for the other two, angle L and angle M. So whatever they are, they have to be the same because it's isosceles. So the same side angles, like angle K and angle L, they have to be supplementary to each other. So if angle K is 50, then that means angle L has to be 130. And angle L and angle M are congruent to each other because they're base angles of an isosceles trapezoid. So that's going to be the measurement of the other angle as well, 130. So now we can start plugging in the fill in the blank stuff. Now that we've thought it through, we can look back at this stuff and say, okay, well, that's how I thought about it, and that's what I would have to do. So we know it's an isosceles trapezoid, so the base angles are the same. The same side angles have to be supplementary simply because we have parallel lines with a transversal. And so that's how we got angle L or angle M, whichever one you wanted to find first. And since L and M are the same, again, congruent base angles, there we go. All right, so I want to go ahead and pause here. Go ahead and pause the video and answer these two questions. And when you are finished, hit play and come back and see how your work compares to mine. All right. So in example one, this is going back to that one that we saw that we showed it was a trapezoid by using the slope formula. Well, now we're taking one of those points and we're changing it to a different location. We're taking point E and moving it to 7, 5. So when I move it to 7, 5, the shape of the figure changes. Now looking at the slopes of D to E and C to F, both of those were still 1/3. So those two opposite sides are still parallel to each other. But now when I look at C and D and E and F, well, there I get another set of sides that have the same slope. So we've changed the quadrilateral from being a trapezoid with only one set of parallel sides into a parallelogram because both opposite sides are parallel to each other. Now looking here at find the measurement of angle C, A, and D. Well, B and C are congruent to each other because they are base angles of an isosceles trapezoid, so that's why it's 135. Finding angle A or angle D, well, angle A is supplementary to angle B, so if I subtract the 135 from 180, that gives me angle A to be 45, and angle A and D have to be congruent because base angles of an isosceles trapezoid are congruent, so that's how D is 45 also. Now here we're looking at something I briefly mentioned earlier, something called the mid-segment formula. Now in a triangle, so if we have a triangle, let's say A, B, C, where this is a midpoint, this is a midpoint, and we would call this M and N. Well, one of the characteristics that we saw about a midsegment of a triangle was that it was parallel to the third side of the triangle, and it was half as long as the third side of the triangle. Well, a midsegment of a trapezoid has similar features about it, but they're not identical. Just like in the triangle, the midsegment will be parallel to the bases of the trapezoid. So MN is going to be parallel to AB, which is parallel to CD. Now, we're not going to really be spending too much time thinking about the parallel aspects of it, although you might want to look at the angles sometimes, so knowing that they're parallel could be helpful. But particularly what we're going to be looking at is figuring out how long something is using the relationship between the lengths of the bases and the midsegment of a trapezoid. Well, in a triangle, the midsegment is half as long as the third side. Well, here I'm comparing the midsegment to the lengths of two bases. And in this case, it's the length of the midsegment would be the average of the two bases. Now, I want to point out here, they're specifically using A, B, and C, D in this example because that's how they labeled the vertices of the trapezoid. Now, if you were going to look it up in a textbook, or if you were going to Google it, or if it was on a formula chart somewhere, this is more appropriate for what you'll actually see, where it actually says base 1 and base 2 is equal to the mid-segment. So just keep that in mind when you go forward working on these types of problems. Now let's go ahead and start working this out. Now again, one thing I really want to point out before we begin, here I have a base that's a whole number, here I have a base that's a whole number. Well, those whole numbers could very easily be expressions instead. Okay, now I'm just making those up. I don't know if they're actually going to equal 16 or 9 or whatever. I'm just saying that the lengths of the bases or the length of the midsegment, instead of being a number, they could be an algebraic expression, just like we've seen with every other figure that we've studied in geometry so far. Well, looking here, we're going to start with the formula for the midsegment. Now again, here we're substituting PQ and SR because those are the bases of this particular trapezoid. Usually when you start writing it out, if you write the formula first, you would simply say Mn is equal to half of base 1 plus base 2. That's how you would start it, and then you would plug in your numbers or your expressions or something like that. So now we're going to plug in the 16 and the 9 into those parts in the formula, and simplifying, we get 25 inside of the parentheses and half of 25. It gives me 12.5 for the length of the mid segment. So go ahead and pause the video at this point and work out problem number 3, and when you're finished, go ahead and hit play and compare your answer with mine. Alright, so here we're looking at the mid-segment formula. Again, we want to know how long is segment MN when I know the lengths of the bases. Well, starting off with the formula, the half of base 1 and base 2, substitute your numbers, 12 and 13, or 12 and 30, I should say, for the bases. Combine your like terms inside the parentheses, and we get 42. Half 42 says the mid-segment in this case would be 21 feet. Now, the last thing that we're going to take a look at here are with kites. Now, one of the characteristics about kites, and I mentioned this at the very beginning of the lesson, is that the diagonals are perpendicular to each other because essentially the non-vertex diagonal and the vertex diagonal, well, let me back that up. The vertex diagonal, which in this case would be diagonal BD, is essentially the altitude of the isosceles triangles. So that means if it's an altitude, it has to be perpendicular to the base, which AC would be the base of either isosceles triangle that we see in the kite. Now keep in mind, because those are perpendicular to each other, essentially we're dividing the quadrilateral into 4 right triangles, meaning maybe I have to use trigonometry, maybe I have to use Pythagorean theorem, maybe I have to use rules of special right triangles. Now at this point I feel safe to say I guarantee you on a quadrilateral that has perpendicular lines somewhere, I guarantee you I'm going to ask you a question that's embedded with triangle properties about it. So I keep reiterating that, so I hope you remember. So the last one here is showing you that we have, again, if we look here on the top one, these are base angles of an isosceles triangle, and these are the base angles of an isosceles triangle. So whatever those two measurements are, if I add them together, I get the same number for point A and point C, no matter what. So those two angles of a kite will be the same. And again, if you need to go back to the beginning of the video where I added all that extra information on the kite diagram and be able to have it for reference if you need it when you're working on problems associated with kites. So here, there's not a lot left in the notes, but there's a lot I could we could potentially ask you about kites. Find the measurement of angle T. Well, angle T is this right here, and because it is a non-vertex angle, it has to be congruent to the angle across from it. So angle R and angle T are the same. Well, we don't know exactly know what angle R and T are, but we do know that they're the same, and out of the 4 angles that we have inside of the quadrilateral, they have to have a sum of 360 degrees. So that's exactly how we're going to start setting up this problem. I know that the angles R and T, they're the same. So the four angles together have to have a sum of 360 degrees. Now because angle R and angle T are the same, we're going to replace angle R with angle T again here in this second row of our equation. And substituting your numbers gives you 88 and 70. Combining your like terms gives me 2 of angle T's, and the 88 and the 70 gives me 158. Move the 158 to the left, from the left side to the right side through subtraction, and I get 2 of T is 202. So that means the measurement of angle T, when I divide by 2, is 101 degrees. So this, I believe, is going to be the last problem that you're going to be looking at. Go ahead and pause the video and work out this problem, and when you're done, hit play and compare how your answers look with mine. Alright, so find the measurement of angle G. This is literally just a regurgitation of the last problem. Angle G and angle I have to be the same because they're the non-vertex angles of the kite. So out of the four angles, we have a sum of 360 degrees. So substitute angle G for angle I into the problem. And solving for angle G in this case gives me 100 degrees. So at this point, this is where I would kind of recap all of the stuff that we talked about. But there is a lot of things here, and I don't want to just, bore you to tears. So make sure that you review the properties of the isosceles trapezoids specifically. Memorize the midpoint, or not, memorize the mid-segment formula because you'll need it. And particularly go back and pay attention to all of the extra information that I gave you about kites that was not necessarily asked questions about here, because otherwise the notes would have just been way too long. We probably would have needed to separate it up into two sections, one for kites and one for trapezoids. But until that's it for now, guys. And until next time, thanks for watching and take care.